the future with advanced electrode manufacturing, please.
No.
Okay, thank you very much. Yeah, thank you very much for kind introduction, and hello everyone, welcome to my talk. So in the morning we had a really wonderful talk from AI and gallium nitride, so now we are going to a bit learn about the gigafactory. So this is a topic recently so many people are talking about. So I try to give an overview to understand for everyone from student and engineer and so on. So before talking about gigafactory, I would like to introduce this United Nations General Assembly Sustainable Goals. So it's 17 goals we created in 2017, and every one of us are responsible to bring these goals, to the point by 2013. And there's many topics, and I am responsible for the number 7. So it's affordable and clean energy. So let's see what we did in our research community. So if we look at this graph, so this shows the price of battery dollar per kilowatt. So from 2013, so $800 per kilowatt, and 2024, so we have about 100. So we did a really good job, but we also tried to make it even more affordable. So why this has happened? So why price came down from 10 years ago and now it's 100? So this is because of competition. So many gigafactories are planned, especially in China, Japan, Korea, and here in Europe and US. So it's 2022, so the planned gigafactory is like 700 gigawatt hour, and by 2030, so many plants it's become like 10 times, so it's like 5,000 gigawatt hour. So if we look at the planned gigawatt factory in the Europe, so this shows about 1,400 gigawatt hour is planned to be built. But if you look at 2023, so it's like 1,897, but suddenly dropped to 1,400 because they cannot survive. It's really big competition, especially with China. So they have resource, they have knowledge, and we in Europe and US almost behind them. So it's really difficult to compete. And if you look at another part of this graph, so this is Germany, which is planned for many gigafactories. So one of them is in the Berlin, which is Berlin actually. So they are building battery for Tesla. And if we look at the next graph, so this is for US. US also is almost similar to Europe. They have planned for 1,500 gigawatt hour. So different state they have, different company, but we don't know how much will we survive in the near future. And the next one, sorry. So this is Asia. So you can see the China gigafactory plan is 2,400. So it's a lot of company, already established, and they also have plan. And besides China, Japan and Korea also are really active, and they have some gigafactories is working, and some also is planned for future. And this is the distribution between Asia and Europe and also US. And the green part actually is those already established, and the red one is just planned. And if you look, the Chinese companies already they established very well in this area. Okay, yeah. So let's have a definition of the gigafactory. So this is Giga Berlin, so it's really huge building, and inside this building, so they produce battery. And so it's gigawatt hour per year. So what we are talking about, if it's factory is like 100 gigawatt hour is per year, so it's production. And inside this is really interesting. If you look at this chart, so this is one line. So at the beginning, the material came from the supplier, so which some company only produce cathode, some produce anode, and then the gigafactory buy it and bring it here to do the mixing first, very well mixing, and then make a slurry, coating, drying, and then press it to make really high energy density electrode. And then we have further more step for cell production. So the first part is electrode production, which is my expertise, and the second part is more system level, is cell production and module, development. Okay, so let's have some calculation here. So I try to calculate some capacity from different cars. So from Tesla Model 3 to Volkswagen e-Golf, so they have different, capacity in the car. So the smallest one is e-Golf is like 40 kilowatt hour, and the largest one is like Tesla is 100 kilowatt hour. So then based on this we can calculate 1 gigawatt our factory, how many battery pack they can produce. So this is a battery pack. So inside this battery pack has different module. And inside the module has many cells. So it's really complicated. And based on this graph, so we can calculate 1 gigawatt hour factory can produce 10,000 to 25,000 battery pack per year. Okay, so this is some example here. Now we can go to see some example. So the first one here is Tesla. So the battery pack is like 500 kilogram, and the volume is 370. And inside this battery pack has 16 modules. And every module has 440 cells inside. So imagine a big, battery pack, how many cells is inside. And if we look at the next one is BMW i3. So this is the cell from Samsung. Here is cylindrical cell is used. This one used prismatic cell. And inside this battery pack has 12 cells per module, so it's a lot of cells. But this cell is really small, about 50 grams, but this one is about 2 kilograms. And the next one is pouch cell, and this is from a Japanese car, Nissan Leaf. So every cell is about 1 kilogram. So they have different type of cell, and they have their own reason why they use cylindrical, why they use prismatic, and why they use pouch cell. But inside these three cells, cylindrical, pouch, and prismatic is similar. So they have anode, cathode, electrolyte, separator. So only the shape is changing. So let's have the next slide. Yeah. then we could have a close look inside this cell. So this is inside the cell, and those line is anode and cathode, which is separated by a separator. So this is anode, the copper one, and the aluminum part is cathode. It's double-side coating, and they are really compact. And the separator is for just doing not short circuit inside the cell. Okay, so now we can go to do some information regarding different type of cell, and this is cylindrical cell. So cylindrical cell is one of the oldest one and almost the best one, because the manufacturing cost is very low, the durability is really high, and excellent thermal management. So how we can do the thermal management? Of course, one drawback is the space management, because of it's cylindrical, so we could have some more space inside. So that is a drawback for energy density, because if we have some less space inside without cell, then energy density of the cell would be less. But it's the good things, because we could manage the heating, because every cell during the charge and discharge getting heat. Then the managing the heat is very efficient with these cells. Okay, the next one is pouch cell. So this is the format of pouch cell. Is the cell we are using in our cell phone and some laptops. So the application here is different. And here use aluminum foil as a housing. Then is not really strong. But the managing inside the cell is really good, so we can use all the space. So the drawback again came back to the heating managing. And one more drawback from these cells is swelling, because the mechanical stability is not really high. But at the beginning, before go to the market, so we do the formation, because at the beginning some gas is produced, then we take out the gas, and then we can seal it and then go to the market. And the next one here is prismatic. So you can see managing space is really nice. So in terms of that, it's really good. And the price is between the pouch and cylindrical cell. But the drawback maybe came to the thermal management, because if we use 2 kilogram cell, then in the middle of cell some heat is producing and it's really difficult to cool it down. Okay, and then next slide. Yeah, so some common application for cylindrical, for power tools, and Tesla also using cylindrical cell, flashlighting, and pouch for smartphone, tablet, and so on. And prismatic also for EV cars. So for example, Volkswagen is using prismatic cell in their EV cars. And some comparison here. So in terms of the cost, so cylindrical is the best one, durability also is the best one, but has that problem for volume, space management. Okay. Then came back to here. So as I mentioned, so the common material or component inside the cell is electrode. So let's see how electrode is produced. So it's anode and cathode, active material, and inside the cell is with separator. Okay. This is really slow. Okay, come back to here. As I mentioned, electrode is producing from the mixing to the coating, drying, and also calendering and cutting, and again one more drying. and every part has a lot of optimization. So I am teaching in this course, and every part I teach 1.5 hours. So it's a lot of optimization, a lot of things we should consider. It's not easy to put the material and then mix it and go for electrode production. So if you see the next one, many things we should consider, and then next one, a lot of things. And this is again the general assembly. And here is one interesting graph. So this is made by Fraunhofer in Germany from this website. So it's showing the energy or the cost here per process. And if you see the cell production, so injecting electrolyte is really expensive. So we make electrode, which is the heart of the battery, is not really too much, but only inject the electrolyte. So we had project for only injecting. So there's many optimization we should consider. The next one is energy consuming, is drier, is more consumable energy part, which now goes for the dry coating. Then we don't need to put dryer. So we mix the dry powder and then coat it directly on the electrode, which is the new technology nowadays. And you can see here is many process to make one cell at the end or one module and then a battery pack. Okay, so some summary here is from raw material to manufacturing and end of life, so to have different challenges. So expensive material, lithium, cobalt, and so on. Then new technology came, and this is beyond lithium. So you also probably heard about sodium-ion battery, solid state, and also metal sulfur battery. So we are working on the solid electrolyte and metal sulfur battery, and that is one of our recent publications. And this would be the future of batteries beside lithium-ion batteries. So lithium-ion battery remain, but this technology they can find, their market. Yeah. Thank you very much.
Thank you for the presentation, and maybe now we have time for one question, but short question, short answer.
Very short. So what is the percentage of the power of the energy you lose in the heat?
Yeah, I don't have any number in my mind, but
okay.
It's definitely based on those calculations. Every step, has different power or energy consuming. So as I mentioned, the dryer is really the biggest one, because if you go to the current gigafactory now, dryer is like 100 meters.
Now, what I mean, if you have a battery, if you use this battery, it produces heat inside. You just told that you have a...
Yeah, that is thermodynamic. So based on the thermodynamic, some heat is producing, but that is not really too much.
Okay, good.
Yeah.
Thank you again. And if there are more questions, please during coffee break. Yes.
Yeah, welcome.
And now the next talk will be given by Zurich Khudaverdian, and the topic is analysis of photoelectronic processes in silicon structure with opposing potential battery.
Я должен извиниться, в основном аудитория русскоязычная. Позвольте мне на русском выступать. Основные моменты уважаемый мною Сидоренко переведет вам на понимание.
Окей, да.
Извините.
Пожалуйста.
Значит, сегодня я представлю новый прибор. Исследование по частям докладывалось в разных конференциях, в том числе здесь, в Молдове. И сейчас более обобщенные моменты основных функциональных процессов я вам покажу на вашу оценку. Это основные аспекты нашего исследования. Исследовалась трехслойная структура N плюс P, N плюс конфигурации, и здесь есть некоторые особенности. Хотя сама структура транзита подобная, как будто биполярный транзистор, но есть следующая своеобразность, это то, что у них области объемного заряда обязательно смыкаются. Это мы так посчитали и получили технологически, и подтвердили экспериментально.
Three-layer structure. The most important peculiarity of this three-layer structure is that the charge poor layer are crossing of this three-layer structure.
Вторая особенность то, что имеет два вывода. Один с поверхностного перехода, второй тыльного перехода. Здесь показаны эти выводы цифрам 1 и 2. И тема в том, что освещение идет с поверхности, проходит через первый, а потом через второй переход, и, соответственно, длинноволновые и коротковолновые излучения по разной пропорции будут поглощаться в этих областях объединения. Это дает своеобразие данной структуры в плане выходных характеристик.
One more peculiarity of this three-layer structure is that the whole structure is transparent for the light. That's why light penetrates to the first layer, penetrates later on until the third layer.
Понятно, что эти переходы могут иметь разные высоты потенциальных барьеров, а могут быть равны. Вот эти аспекты дают разные функции. Теперь, если переходы имеют разную высоту потенциальных барьеров, то эту разницу как раз та часть напряжения, это несколько десятков милливольт, прикладывание которого происходит в смене знака фототока. Значит, первая особенность то, что происходит в смене знака фототока в таких структурах. Здесь показано вот эти смены знака и, соответственно, длина волны, при котором происходит эта смена. Причем точка смены знака от внешнего напряжения строго линейный характер имеет. Это позволяет по наклону этой линейности, по тангенсу угла этой линейности определить неизвестную длину волны. И еще один особенность то, что это не всегда происходит. Происходит только тогда, когда есть разница высоты потенциальных барьеров. Скоро поймем, почему это так.
The other important peculiarity of this structure is that the potential barriers are different, and the wavelength of the light linearly depends. The voltage is linearly dependent on the wavelength. That's why you can estimate the wavelength of the light by measure of the linearity of this dependence of wavelengths from the applied voltage. And the voltage can change the sign.
В данном слайде показана волтамперная характеристика при освещении тех образцов, у которого нет разницы высоты потенциальных барьеров. Как видите, по левой стороне есть насыщение первого и есть насыщение фототока второго барьера. И это четко здесь изображено. И что важно, по правой стороне есть вот амперная характеристика при малых значениях напряжения, две кривые. Одна кривая красная, это когда есть разница высоты потенциальных барьеров. И здесь около 50 милливольт есть фото-ЭТС данного данной структуры. И это именно та величина, которая сравнима с разницей высоты потенциальных барьеров. Тогда фото-ЭТС есть. Но когда эта разница отсутствует, фото-ЭТС тоже отсутствует. Это синяя линия приведена на этой же графике.
In case if you have difference in the height of potential barrier, the voltage photo response is 50 up to 50 millivolts. If there is no difference in the potential barrier height, there is no photo response.
Вот здесь спектральная характеристика тех образцов, у которого нет разницы в потенциальных барьерах. Что особенно? Спектральная характеристика светочувствительности, как видите, по току, и четко есть длинноволновые и коротковолновые максимумы. Коротковолновый соответствует приповерхностному ПМ-перехода, длинноволновый соответствует тыльного ПМ-перехода. Теперь, вторая особенность. Очень высокие светочувствительности. Как видите, когда ширина базы D равна 5,5 микрометр, а точка стыковки находится 3,9 микрометр глубину, тогда мы имеем высокую чувствительность, особо в коротковолновой области, 4,2 ампер на ватт.
Very high sensitivity, photosensitivity is up to 4.2 ampere per watt.
А коротковолновой области 1,2 ампер на ватт. И почему это мы называем высокой? Потому что, например, широко используемые фотодиоды фирмы Хамамацу, а мы знаем, что основные ноу-хау находятся у этой фирмы, у них высокая фоточувствительность находит 0,7 ампера на ватт. То есть 4-5 раз меньше, чем наши образцы. И вторая особенность то, что есть коротковолновый и длинноволновый, здесь не приведено. И точки максимума можно изменить технологическим путем, сделая разную глубину перемещения или стыковки этих истощенных областей.
They have a technological approach which allows them to change the width of the charge pore layer, and corresponding to this change, they can change the short wave maxima. That's they can manipulate the short wavelength maxima using the more deep doping or less doping.
В используемых фотодетекторах есть один максимум, основной, и это находится в области собственного поглощения. У нас это находится в области собственного поглощения длинноволновый максимум, а коротковолновый это зависит от глубины приповерхностного слоя. А то, что зависит от глубины приповерхностного слоя, на этом слайде показано на левом рисунке глубина стыковки 2,9 микрометра, то есть находится вблизи поверхности, на втором рисунке 3,9 микрометра, то есть находится в более глубокой части. А это приводит к тому, что в первом случае коротковолновое поглощение сравнительно мало, потому что область истощения перехода находится вблизи поверхности. А длинноволновое поглощение значительно больше. Поэтому высокую чувствительность получена именно длинноволновым. Здесь, извините, доходит до 11 ампер на ватт. Это практически больше 10 раз больше, чем в фирме Фамамацу. А второй рисунке, наоборот, X7, то есть точка стыковки глубже находится, и при поверхностном слое поглощается большее число коротковолнового излучения, поскольку у них поглощение идет по экспоненциальному закону, и это позволяет большую чувствительность получить в коротковолновой области, чем длинноволновой. Вот эти особенности двух технологических процессов, как итог двух технологических процессов, приведено здесь.
Нажми любую кнопку. Нажми любую клавишу. Нажми.
Что, я это могу нажать?
Не хочешь.
Так, да, пусть. Ну, здесь тоже самое. Здесь общая спектральная характеристика, где ярко видно два максимума, коротковолновый и длинноволновый. И смены знаков фототока.
The spectra obviously demonstrates two maxima, short wave length maxima, which correspond to surface absorption, and long wave maxima, which correspond to penetration of the light and absorption in the volume of the structure.
Минимум спектрального фототока – результат того, что два барьера создают фототоки противоположного направления. И в зависимости от того, какой фототок больше, тот и играет основную роль. А когда они близки друг к другу, взаимокомпенсируют, у нас получается минимальный фототок.
Long wave and short wave, they have opposite sign. That's why the minima in the middle correspond to the overlapping of these two processes. That's why it is the result of the opposite sign of the photocurrent.
Может быть, перейдем к выводам?
Yes. Conclusion. 1 минута осталась. 1 минута осталась. Надо заключение.
В общем, там, где очень высокая фоточувствительность, мы связываем с внутренним усилением фототока. Если вопрос зададите, я объясню. Здесь, там, где нет высокой фоточувствительности, есть смены знака фототока, у нас есть возможность спектрофотоматическое устройство, как использовать этот фотоприемник. Одним фотоприемником получить спектр излучения. Здесь показаны все возможные виды спектрального анализа, и они сложны. В общем, масса недостатков по сравнению с тем, что мы предлагаем. Дальше это элементарная схема, по которому излучение заходит в образец, от него выходит с информацией уже внутреннего состояния этого. Здесь приведена алгоритм нахождения тяжелых металлов в земле с помощью нашего фотодетектора. Здесь соответствующая схема, блок-схема, по которому можно получить. Мы реализовали этот принцип на конкретном приборе. Что мы делаем? Мы вот амперную характеристику, цифровые данные волтамперных характеристик подаем на вход алгоритма и на выходе получаем спектр излучения с информацией из той среды, откуда идет излучение, где поглощается излучение. Вот это полученная волтамперная характеристика, вот это пошаговое дается напряжение, и поэтому алгоритм получается зависимость интенсивности излучения от длины волны, то есть спектральную. На левой стороне подаем разные цвета и получаем на выходе, например, вот такую, для зеленого, кажется, получаем вот такую спектр зеленого светодиода, который очень близко, ну, соответственно, выводы. Извините, у нас мало времени.
Just one statement. This is, from a device physics standpoint, this is a very clever way of band gap engineering. So you make opposite structures, apply voltage, and then you can control the spectral response. So essentially a very clever way in which he has calculated the doping. So I just wanted to add that.
Thank you.
Thank you very much, Professor Khudayberdian. I have a short question to Professor Vasyashta, who is also a co-author. Imagine that we have detected heavy ions in the soil, which are very bad for all living beings, for us, for plants, for everyone. With this method, which is very precise, I appreciate it. What should one do? How to clean soil of contamination with heavy metals? So do you have any practical idea? Further step, next step.
If you can tell me what that contaminant, of course we know what those contaminants are.
Yeah.
So this is a proof of concept device to detect what's there. From remediation standpoint, may it be a metal, may it be a plastic, may it be a herbicide, pesticide, all different kinds. So I cannot give you a general answer unless I know what those contaminants are. But this is a proof of concept device which he calculated, and it's those device, those TO3 or TO5 cans. Is it TO5 or TO3? Those cans? Okay, irrespective. They were fabricated for us in Latvia by a company. It's an application-specific IC lab. So they fabricated based on the specification. But as mentioned, this is a proof of concept device. But in terms of detection, we can detect different types of contaminant, even in transparent environments.
Yes.
However, to answer your question, if you tell me what contaminant you have in the soil or in water, I can tell you how to mitigate this.
But this is the preliminary stage,
Right, exactly.
which requires then further analysis. Thank you very much.
Thank you again for the presentation. And the next talk will be given by Vadim Murar with the topic Impact of Precursor Concentration on Topology, Wettability and Electrical Property of Zinc Steam Oxygen Films obtained by spray pyrolysis. Please.
Thank you very much. Hello everyone. My presentation consists of introduction, preparation of zinc tin oxide film, surface morphology IFM analysis, wettability of these thin films, X-ray diffraction, electrical study, also deconclusion. Zinc tin oxide has attracted significant attention due to its very interesting properties. Combine good electrical conductivity with optical transparency, make it particularly suitable for transparent conductive films. These films are crucial for modern electronic devices such as solar cell, photodetectors, catalysis, and batteries, and more else. This thin films was obtained by spray pyrolysis method. Here we can see the schematically the method. For this we use two precursor solution. One is tin chloride and zinc nitrate. These two solutions we mix it in alcohol ethylic, so and obtain 3 molar concentration. First one is 0.05, the second one is 0.15, and the third is 0.30 molar ratio. So pyrolysis process consists of 4 etaps. The first one, the spray nozzle form the droplet. Then this droplet, when touch the heat substrate, the substrate is heated up to 600 degrees. This droplet is evaporation, then decomposition, and in the final process we obtain the thin films, in our case zinc tin oxide. We investigated surface morphology. This provide the roughness of the films, and as we can see in the table, the root mean square at 0.05 mole ratio is 0.6, and as the molar concentration increases, the roughness also increases. The same behavior is inspect for the mean roughness. It's the same situation at low concentration. From low concentration to the high concentration, we can see the same behaviors. IFMBE studies also demonstrated that at low concentration we have our film present the hydrophobicity at 120 degrees, and when we increase the concentration of molar in our precursor solution, we can see that this degree also increases to the 124 degree. Our past studies demonstrated that when we have ratio of molar zinc to 1 thin, we have two phases. One is thin oxide, and the other one is zinc thin oxide. It's very difficult to obtain just one phase, but we can do it optimize our condition of deposition, such temperature, molar concentration, and speed of the gases for optimize this condition. We demonstrated that this MSM structure work as we made electrical study. So in this investigation, we demonstrated that as from the electrical study, we don't see the behavior as IFM or Veaceslav studies. Here we have already another situation. First of all, at 0.05 mole we have lower current, and the maximum current we have at 0.15 mole. This result suggests that the material responds differently to illumination depending on the precursor concentration. At the precursor solution at 0.15 mole, an optimal balance between charge, carrier density, and material structure is reached in the zinc tin oxide. So we made the report current elimination to the dark current at 3 volt, and we obtained 35 this coefficient. So in conclusion, surface roughness increases with concentration at 6 to 12 nanometers. Wettability improves with high hydrophobicity from 119 degree to 124. Best photocurrent to the dark current ratio, it's achieved at 0.15 mole. And spray pyrolysis offer a low-cost technique, scalable fabrication route for production films for application in optoelectronics. Thank you for your attention.
Thank you for the presentation. If there are questions, please, Professor Fomin.
Very short. Thank you very much. You indicated in the last slide the best photocurrent to dark current ratio. 34. This is the best for your sample.
Yes.
Can you compare this figure of merit to other systems, to other materials which are available for optoelectronics? Where are you now? Are you pioneers, or you have the same level as other materials?
Yes, I can compare with the zinc oxide, for example, and for zinc oxide, this ratio is around 120. Yeah. So I need to improve my structure to increase my this ratio.
Okay.
Yeah, but zinc oxide is unstable on atmosphere. There's these oxygen vacancies which are always kind of switching on and off. How is it with your samples? Are these stable? I mean, tin dioxide is stable, and is this zinc tin oxide stable?
Yeah, if you compare zinc tin oxide with zinc oxide, this films is more stable. Yeah, it's in atmosphere and chemical stable, yeah, it's more stable.
Thank you for the presentation. And the next talk will be given by Alexander Kudryashov with the topic 2 dipole-dipole interaction emitters in a moderately strong laser field.
Thank you very much. This is a topic in quantum optics. It concerns two atoms, two-level atoms. So we have a system. It's inside the reservoir. It's not just vacuum, of course. We can never ignore our vacuum. But we also have a strongly driving field. This is a laser, basically. So we'll see how it plays and what we can learn from this setup. So actually what we're studying is the resonance fluorescence regime, and in very particular regime, and I'm going to go through all of them because they're important. I can tell you that if you just change a little switch, you can create a new paper. But our papers, it's not a simulation. We do everything analytical, so pen and paper. That's why we go very carefully from the things that were already built in the past. For example, like the model triplet. Everybody knows that, you have an elastic scattering where you will go from the ground state to the excited state. If you have a driver, a field, a strong laser, let's say. Okay, so then you're gonna generate this transition, but in addition to that, if you're gonna look at your spectrum, you're gonna see sidebands symmetrically to your elastic transition here. And resonance means when your laser is equal to the transition energy difference. So your sidebands will tell you that, well, actually you have kind of like a Stark effect, or if you think in a magnetic language, it's like a Zeeman effect, but okay, let's not really change the topic. So, and this split of the ground and excited states, they'll have their own frequency. We call this the Rabi frequency. So basically, we created 4 levels just by applying an external field. And this is not even looking at how the vacuum interacts, because it's a little difficult. In what sense is that even if you have a vacuum and just an atom without any laser, you'll see that your electron cloud is actually displaced from the nucleus, from the center of the nucleus. So you created a dipole, and this dipole, of course, we're gonna start oscillate, and this will populate the excited state and the ground state in the vacuum, right? I'm not even talking that your ground state has to be very special and your excited state as well. Your ground state has to be symmetric. Your excited state has to be antisymmetric. Your ground state is basically an S shell. Your excited state, most simple antisymmetric state would be a p orbital. And the p orbitals, they don't have length shifts. It means that in vacuum they don't split, but your ground state splits in the vacuum, right? So by applying no laser, you'll have 3 levels. But we don't consider the lamp shift because it's not very symmetric, right? It's not very nice. We like to work in pairs 2, 4, and then just take away antisymmetric states. So, okay, this is the 50s, right? They created this elastic transition with the sidebands, and what we do next is actually we're gonna look inside this dipole approximation. Is that by using the power ZML Willy transformation, we're gonna ignore our chosen vector field, right? So if we square it, we say, okay, it approaches 0, but we're going to keep the dipole. So the dipole will be the distance between the center of the nucleus and the center of the electron cloud. It's very important to think that your electron structure, your energy level structure doesn't change, right? But this cloud kind of pushes into your p shells, right? So it's not that we are changing the architecture of our of what we know about atom states, but we just try to create some models, and we think that the dipole model is very nice. That kind of explains us why our cloud oscillates, and it oscillates. Sometimes the direction is similar to the electric field, and in this case it's vacuum, but it can also be your laser. But I'm going to show you how you can ignore your laser. It's not that you ignore it, just going to the reference frame of the laser. So basically this is what we do. When we construct our Hamiltonian, first part is we consider our reservoir. So this is all vacuum, right? We cannot forget about it, but the minus omega laser, it just means that we're in the reference frame of the laser. And what does it mean is that here the transition on the Z scale, think about, I don't know, spin up, spin down, right? And the omega 0 is your energy that you have to give to go to flip the spin, right? In this case, we lower the energy for flipping the spin by providing a strong electromagnetic field or laser. And so our Z scale, the magnitude on the Z scale changes as well. How does it change our X and Y scale? Basically, we see that our spin actually is tilted by 2 theta, and this is of course in a spinner in a physical space. A full rotation is actually 180 degrees, 360 degrees would be 180 degrees in a vector space. But since our vector space is like a complex space of 4 dimensions, it's very, very hard to do those analytical methodologies, right? So we still try to keep to physics. So we use the block sphere, and in this case, we use a very interesting thinking from Cohen-Tanucci, because it's his approach where you go into the frame of the laser, so your amplitude of flipping the spin changes, and then you forget about the laser at all. And on your Pauli X matrix, you consider that you have a Rabi frequency. So we already saw the Rabi frequency. It's not new. It's introduced by Rabi, of course, but it was very nicely introduced by Molo triplet into his spectrum. So I think this was even experimentally demonstrated. So the distance, this would be your elastic part. So this would be your omega, and the distance here would be your Rabi frequency. So you, when a state splits, it has its own oscillation beside the flipping of your states, right? And then you just create 4 different combinations. Plus Rabi, this is it, minus Rabi, here, the smallest, it would be this. And then the elastic parts, which should be a little bit higher, so because they're double just. So the intensity is just, it's more. Okay, so as I said, we now in this frame, we just have an oscillation on the x-axis, and this is, as I said, between the state that is split, right? So this is not transition of your initial ground and excited state. Okay, so we talked about the laser. We talked how to deal with it. We talked that we have a different amplitude for our the difference between the ground and excited states, and this difference we call it detuning. and when the detuning is 0, meaning that your states coincide, right? This is what we call resonance fluorescence. And yes, so I explained the first part of the Hamiltonian. The second, this is the Hamiltonian of our atom with the detuning, right? Because the frame of the laser created our new Hamiltonian for the atom, and this is just one atom because in my paper we have 2 atoms, and this is the term that I just left it for enthusiasts just to look in the paper because it's similar thinking, right? An atom is gonna act on another atom by its own electric field, and this we call that it creates a dipole-dipole interaction. But before talking about dipole-dipole interaction, which is just, for every state that you found for one atom in a laser field, in a vacuum, you just split it, every state into 2, right? So this factor, you can leave it for later when you just understand your system. And the last one is just how the vacuum will interact with your dipole. So here, it's not that the dipole, of course, we have 2 dipoles. One dipole because of the laser, another dipole because of the vacuum. Now, since we're in the laser reference frame, we don't have this dipole from the laser. So it leaves us to take care of just one dipole. And it's very nice because here, the dipole is coupled with the electromagnetic field of the vacuum, and the GK just has the polarization vector as well as the volume of our reservoir, and it matches the dimension of the dipole, and this dipole is a vector but also an operator. I mean, it's just the amplitude of the operator that just tells us if your atom is in excited state, and it doesn't matter which excited state split, but if it goes down, it will emit a photon. And this is why the coupling is like this. You can even have that your excited state relaxes, and it actually absorbs a photon. But, this is what we call the rotating wave approximation. And you can show it in different ways, but also from the graph, you can see that you can ignore them. It's not that you can ignore them, but they're too fast, they oscillate so fast that when you look at your system, you don't see it. It's like that, because if you look at these transitions and how the dipole oscillates, those things, it's like, it's like this a factor that you can actually ignore, because it's not influencing. It averages to 0, and it's another one when your transition goes up, it emits a photon, right? It's like very counteractive, but it's possible because, although its average is 0. Okay, so here, as you saw, our spin, right? It's not on the z-axis, but we needed to project it on the z-axis, like usual, and that's why we have this laser, the radio frequency, and then the detuning. So this projection. So imagine the Bloch sphere, and then your states that are like opposite aligned, it precesses, right? So when we project on the radio frequency on the detuning, this would be your transition from lower to upper, and if you're lower or upper, then you have additional transition. So it's like you go one dimension and then another dimension, right? So this projection.
We should go to the conclusion.
Yes. So this creates our different bases. This would be our bare basis, and this is the basis that is tilted. This is things that precess, right? So when we do that, we create new bases. We rewrite the Hamiltonian. The creation and annihilation operators of the atoms are also projected, as you see, and we kind of have this trigonometry, but don't be scared, it's very simple. If you look into the Bloch sphere, how you project your system that is processing, you know, it's very simple. Just one dimension and then another dimension. And this is guaranteed. This is guaranteed that every state will always spin, will transition, and this will transition from like the original state to the other state. But of course your new system doesn't know. So you always have to sum all your transitions. Okay, so here this is split because of the Rabi. Here it's split because you add another atom. We do ignore the antisymmetric parts. So basically, like here, but it has like a caveat. I cannot go into it right here. So this would not be all your states. Here it's missing the antisymmetric states, but it averages to 0, so we can ignore it. So as you can see, you create new states from 2 atoms and with different transitions. Okay, so all in all, you go to the master equation and then you create your spectrum. And why this is important? If you have resonance, you don't see this elastic part. But what is this? This is the distance of the Rabi frequency. This is when you're in a state and you just transition relative to the bare state, right? But what is this? This is exactly the dipole-dipole interaction. And why this is interesting? Because here you can measure how distant one atom is compared to another. So you can measure the interatomic distance, which I think is very interesting. It's a very interesting way to do real measurement just by looking at electromagnetic interactions and how the level splits by using the Molo triplet and then the coherent energy addressed state formulas. All right, so thank you very much.
Thank you. Unfortunately, we have no time for questions, and we will go just now to the next talk, which will be given by Oleg Lupan. Yeah? Oleg Lupan.
Okay.
With the topic polymer-coated cadmium doped zinc oxide nanostructure for dual sensing of volatile organic compounds and battery vapors.
Okay, everybody. So today I will show you some of our results made in collaboration with Kiel University, Technical University of Moldova, especially Center for Nanotechnology and Nanosensors, and few departments from Kiel University. So it's about polymer coated doped zinc oxide nanostructure for VOC detection and for battery. So, like it was presented by Dr. Mihai, a lot of batteries now are growing up, so it's very important to have also safety for these types of applications everywhere, especially when a huge amount of energy is stocked in a small space. Another sources of volatile organic compounds are production from vehicles and from industrial process, and now we can see even from our neighbors it's even much more of this. So what we are planning to do and what we are trying already to do really is to develop some new types of sensors which are able to detect also these volatile compounds from the batteries and from different applications, including biomedical or other types. So this so-called hybrid materials, we are trying to using these synergetic properties from different components. So we use oxides like traditionally we are working in this field for many years, and recently we started to use some polymer or organic layers by a new approach, covering on top and try to detect, for example, these types of vapors. So from our previous results reported in materials today, 2 years ago we used some heterostructures like it was shown today for photodetectors also, but we are using for combining these types of oxides to get a much better response and real detection. For example, in first line, first row, we have detectors for ethanol based on this heterostructure of mixed oxides and zinc oxide. Next, middle row, we have covered these types of heterostructures with polymers. And in this case, if we can compare both lines, we can see that selectivity was changed from ethanol to hydrogen, which is also highly important for biomedical applications. And the next one is by using this type of hybrid materials. We tested for battery sensors, and we found that at different operating temperatures, we have, for example, for uncovered one, we have detection of C3H6O2. This is a volatile from the battery sensors provided by Dr. Mozafa. And another one covered already with polymer. We changed selectivity of these types of sensors, and they really shows sensor properties. So how looks the structures? We have some columnar oxides grown by our technology. We have complete cycle developed, everything is functional. Next, it was used ALDI to deposit ultra thin film of aluminum oxide or titanium oxide. So in all these types of heterostructures, we can get different types of sensors. For example, in propanol and battery sensors for C3H6O2, and then by adding titanium oxide, we change selectivity to C4H10O2, also which are in batteries. And operating temperature is about 350. All these results were published also recently. Nano Energy, highly impactful journal in CS Applied Materials and Interfaces. More details. So in current work, we started to use different types of polymers already, because our colleagues and friends from Kiel University, they are working very hard on these new types of polymers, a very new technique, which I think in the world not so many can make it. So we are covering these sensors with tiny, so the whole process here is represented, but in final we are covering this final sensor structure with polymers. So namely in this case we used PECDMI. This is a new one, new type, conformal cross-link polymer thin films. And it was reported by a team of Professor Faufel and his group. So it looks like this structure. And also this one, it's highly important, these types of polymer, only to fabricate different types of hydrogels. And group of Professor Adelong is working on this to develop different types of engineering scaffolds. And also we have a joint project between Technical University, Medical University, and Kiel University about these scaffolds recently. And our PhD students who also co-author here, now he is in Germany at Kiel University preparing new samples. So what's the idea of this? It's really a new technology which was developed and reported by a US professor and transferred to Kiel by a group of Professor Faufel, and it can cover really large area and highly precisely. So it's about nanometers range. So any types of surfaces can be covered in this way, and it's something like a cooking machine, and the setup is constructed like this. We have this heating filament, monomers, and different radicals are introduced. And finally, we have this big polymer covering on this any types of substrates. So here we have morphology of our columnar films grown by our technology, and then final they are covered. We can see original ones, and the next SEM images we have covered one. We can see that surface becomes slightly more uniform, so it covers completely the whole surface of these layers. Also, it was performed EDX to find doping. Why we used cadmium dope? Because previously we reported nanosensors on this cadmium doped zinc oxide, and they showed very good sensor performances. But for wider range applications, it's better to use some thin films. It's cheaper and more easy to be implemented. So here we have some results for such types of hybrid sensor structures, which are showing selectivity to 2-propanol in this case, and we can show the pulses, they are repeatable, and also by adding this polymer on surface, we can even reduce the response time of these types of devices. Next, we have tested same sensor structures for battery response, battery compounds, and it was found that at different operating temperatures we can change selectivity of these types of devices from C3H602, for example, and to LP30 and others. So this is only one type of device. Some conclusions that sensors can be tuned. These devices can be used for medical applications, for battery detections, and some other. So I also want to say thank you to our team in Moldova, also Professor Tronciu, who is organizer or chair of this conference, and other chairs and the organizing committee. They really did the hard work to organize this team, to organize this event for us. Also, this nice, beautiful photo from Professor Adelung team. We can see here also Dr. Mozafai is here. Recently we have a joint Horizon project between our university, where our PhD student will defend soon thesis on this, not on these types of materials. He has another one. I will show the plenary. And the second team is Professor Faufeld. He recently retired, but he still is our very good friend. And Professor Ameli, she took lead of this group, which are working on these types of new materials. But this synergy and combination of work from different groups can generate really new applications. Thank you.
Thank you for the presentation, and maybe we'll have time for one question. Yes.
Thank you very much. In collaboration with Kiel, you have a cornucopia of methods to fabricate such structures. Could you still comment on ICVD? It's not so well known.
Yes.
What is it, and what is the quality of the result?
So this is a really new technique.
No.
It was used from a professor
MIT,
from MIT, USA.
Karen Gleason.
Okay.
Yeah. So she published even books, but after Professor Faufeld took lead in Europe on this technology, only he can do it, and we started to make this joint structure. This is really new, and they saw our results, and they really were happy with this technique, ICVD, which is really new.
Could you describe briefly, just maybe in 2
I will
seconds?
show at the plenary more details about this.
There will
We'll
be
have
a plenary talk, so
plenary talk about this.
Yeah, but it's basically, I would say, the polymer analog to ALD. So there's this initiation, so that only the polymer, so it's pinhole free and coating everything. So and it's shown in this drawing. And I'm as well not an expert, because this is Franz Vaupel and Stefan Schröder who took now over this, but it's pinhole free, and then so therefore the the polymer can only polymerize if this initiation is done, and that's the trick to get it pinhole free and coated.
And this is only one type of polymer.
Yeah.
We use, in plenary I will show you more. Types, we really use different types of polymers, combining with this really shows.
How much of this is done in Moldova and how much in Germany?
Maybe half.
So sensing is most of the time done here.
Oxides also here. We are doing deposition.
And there's a large fraction of Moldovans in German, so it's difficult to
it's hard to split this, but usually, like we know, in Germany and PhD thesis students should write their percentage.
Thank you, and we arrived to the last presentation, which will be given by Katerina Belyaev. Yes? With the title Synthesis, Structure and Property of Linear Trinuclear Cobalt Isobutyrate Cluster with Phenanthroline.
Hello everyone, my name is Katerina Belyaev. I want to present my research work on synthesis, structure and property of linear trinuclear cobalt isobutyrate cluster with phenanthroline, carried out in cooperation with Institute of Applied Physics, with Institute of Inorganic Chemistry from IFMBE. I will start with some information about the importance of this type of compounds. Respectively, this type of compounds can manifest biological relevance, magnetic properties, catalytic activity, redox flexibility, and structural diversity. Cambridge Structural Database reveals a numerous number of coordination compounds of cobalt with carboxylates and have ligands containing nitrogen, sulfur, phosphor, oxygen donor atoms. Such ligands are important because they can influence two compounds for electronic, biological, and magnetic properties. Were identified compounds with linear architecture 17 polymers and respectively 10 clusters architectures. Our compounds was obtained by two different methods of synthesis using cobalt isobutyrate with phenanthroline and dimethyl sulfoxide and acetone by ultrasound irradiation and hydrothermal heating. The first step on our research is obtaining the monocrystal high quality, what can be their structure identified by X-ray diffraction, and determination of crystal structure was performed by Shells 97 and Shells 2014 package. For the SRD measurement was performed on a Rigaku Miniflex 600 diffractometer. Magnetic data were collected using quantum design squid magnetometer. Elemental analysis was performed using the elemental value yield analyzer. TGA spectrum was performed on metal to lead thermogravimetric analyzer. Infrared spectrum were performed on the TIR spectrometer, and Herschel surface analysis and 2D fingerprint plots were performed by Crystal Explorer package. Our compounds is center symmetric, reside on a special position on a crystallographic inversion center. Where central cobalt 2 atom of the cluster is octahedral coordinated by 6 oxygen atom of 6 isobutyrate carboxylate ligands. 4 of these act in a digit-tagged fashion, binding cobalt 1 with cobalt 2 atoms. When 2 have several digit-tagged kilowatt bridging unit. Here we have the crystallographic data for our compound. Molecular structure identified by stated by how phenanthroline ligands, interatomic cobalt, oxygen, cobalt, nitrogen distances, crystal backing along the A and B axis, and respectively XRD analysis indicate that simulated and experimental compound are infrared spectroscopy identified specific group specific regions. For this, we have mass spectrometry for positive and negative mode, that involving maximum peaks for respective cobalt anion and cation. Thermogravimetric analysis indicates that the compounds are stable and first decomposition are at 160 and when at up to 360 degrees. And the compounds are decomposed to cobalt 304, then to cobalt 4. From magnetic measurement, we can observe that our compounds are ferromagnetic non-smell-like interaction and exhibit ferromagnetic interaction between cobalt atoms. For our compounds, respectively, was performed the Hirschfeld surface analysis to identify specific contribution and interatomic molecular interaction. By this analysis, we identified that predominantly we have HH and when found CH and OH type of interatomic interaction. Respectively, we have CC and CH interaction that contribute to extend the cobalt-free fragments to the chain. And conclusion was obtain a new homometallic nuclear cluster using by tools in synthetic methodology. X-ray diffraction study reveal a linear arrangement of three metal centers. The cobalt central ion exhibit a regular octaedric geometry when the periedral cobalt ions exhibit a disordered octaedral geometry. The obtained cluster demonstrate a good thermal stability. The magnetic property indicate ferromagnetic interaction between the high-spin cobalt 2 centers. However, in dynamic field measurement, no outward phase signal are observed. And based on Hirschfeld surface analysis, the contribution of the various interaction resulting crystal 1 were calculated and identified. This allow their importance in construction different crystalline architecture to be determined. Thank you for your attention.
Please questions, if any? No, if not, then we have now a coffee break. And you have a question?
I can ask.
Please, yes. Let's have a group photo now.
Corridor.
Can I ask a question? So what is the main motivation for creating this type of structure?
Я вам хотел что-то сказать. Это не комплексно. Я очень люблю. От вас второй случай после шока, да? Чего я не знаю.
Yeah, which was slightly also very okay, and then first you have to understand of course the structure.
Можно в него нельзя. Ну то всегда у меня там. Тогда туда. Все отлично. Еще, ага. Ага. Вот теперь место.
Conference dinner is tomorrow, today's reception.
Much after leaving, and also the initial polarization of the film. So by growing, these films are nitrogen polar. So nitrogen atoms are here, these black ones here, and the metal atom is here. So this doesn't change over the thermal treatment, so stays stable in the same polarization. Here you see a picture with the most common ferritic materials and where this material is situated. So it has a large polarization, and also it's very stable with the temperature. Yeah. Now a summary of the properties of these materials, or ferritic properties. So they have large thermal polarization, larger than 100 microcoulomb per centimeter squared. They have high coercive fields, 4 to 7 megavolt per centimeters. They have high Curie temperatures, so they have seen larger than 1000 centigrade. And they have low permittivity, which is an advantage in many applications. And they have a stable crystallographic Wurtzite phase. Now, what happened? It's very important to, because of high coercive fields, it's very important to see what happens in very thin films, ultra thin films, so to lower the operating voltages here. And here's an experiment with films from 100 nanometers down to 5 nanometers. They are all ferroetic, even down to this thickness here. And you see, we observe a decrease in the coercive field for the thickness lower than 10 nanometers, and this can be explained by a model developed by Lauber, where the, let's say, dipolling field plays a role, and this appears due to the imperfect screening of the interfaces. And also we see an increase in the switching current here, while lowering the thickness, and this we put on formation of conductive domain walls. We'll talk about that a bit later. Now, talking about these ultrasonic films, we have some TM investigation. So we use annular bright field, STM, because this technique allows us to image very light atoms like nitrogen, so to check the polarization in these films. And it was confirmed that the film thickness is in the range of 4 to 4.5 nanometers, and the grain size in these films is about 2 to 6 nanometers here. And this is an example of a grain where like nitrogen polar and metal polar regions are separated by a domain wall of domain boundary here. Now, I would like to talk about polycrystalline films. So the first films we have produced were polycrystalline, and they have an out-of-plane orientation, but in plane they are completely randomly oriented here. But also we have deposited epitaxial films, and we have two systems. One, epitaxial films deposited directly on n-doped gallium nitride, so single crystal commercial substrates, and another system where we have introduced an additional epitaxial platinum layer very soon. I will talk about that and what are the improvements. Now we checked the structural properties of these films deposited directly on gallium nitride. So this is a epitaxial relationship here shown in this, and we see that there is a critical thickness. So like films lower than this critical thickness are fully strained on the substrate, and the films larger, with a larger thickness, they relax here. So at least this happens for the doping concentration of scandium 28%. This can be different for different scandium concentration. You see the evolution of A and C lattices for different concentrations. And we see that we get kind of lattice match growth condition for a concentration of scandium of about 19% here.
So what are the electrical properties of these films? So here we see some features, particular features in these films here. And we see that basically we have two switching peaks. We see here very clearly in this black curve, also on the positive side. And this it's due to the presence of two volumes in these films. It's a fully strained volume, which is near to the gallium nitride substrate. And it's a more relaxed volume, which is appears for the thicker films, the relaxed volume, and those show this relaxed show lower difference here. So these peaks here correspond to this relaxed, and this one to the strained films here. And another particularity is that because of the let's say formation of space charge region in gallium nitride, we have a voltage drop in these devices, and the peak shape here is widening, the shape in the negative side because of this additional voltage drop, which also induce actually they need larger fields to switch. Now this result was supported by PM investigation here. So you see here that the part which is close to the gallium nitride interface, it's a metal polar here, and this takes the polarity actually of the substrate. Gallium nitride itself is metal polar, and the part of the film which is a copper interface has a nitrogen polarity, so similar with polycrystalline films. This has been also checked with some chemical experiments. I will not insist much on that. And now we have introduced an additional epitaxial layer, very thin platinum, and I will explain you what are the effects of this. So we still have a full epitaxial system, but we have no strain gradient in the ferroelectric layer, so we don't have any more volumes with high strain and low strain, and there is no polarity transition for the earth-grown films, and we have no diffusion zone because we have the platinum as a good conductor, as a bottom electrode this time. And now, this is a structural characterization of these films, also comparison with platinum and without platinum here. So we see those with platinum are more relaxed. They approach the A lattice approaches the relaxed lattice of this material. And because of that, we have a decrease in the cohesive field and reduce in leakage. You see the comparison between this red curve, which is with the platinum, and this black, which is directly on gallium nitride. Now I like to come to another issue that I want to present you. So we see some resistive switching effects in these capacitors. This capacitor here, it's of other type. It's so what I showed you before was all were deposited by sputtering, photon sputtering films. Those are deposited by MOCVD in other group, not in our group here, and they show metallic polar for the whole stiffness here as a pristine, I mean as grown films. They are metallic polar, and we perform some PFM experiments here to see what happens with the polarization and with the conductivity in these films. So these are capacitors with top electrode here, very thin one, so we are going to do PFM in this. And we have the fully M-polar state as a pristine state. We have a mixed state here, so it's a partially switched material here. And we have a completely switched state in the nitrogen polar here. And we observe that these states have different resistivity in this static IV curves you can see here. So in the partly switched state, we have the largest conductivity, or the largest currents here. And we explored more on that, and we have performed some pulse experiment, pulse amplitude experiments here. So you see this curves here. So basically we use a reset pulse. So this reset pulse will switch the material into it's a negative to switch it into M polarity, and then we apply a positive pulse with a variable amplitude, and this is a amplitude on its scale here. So how we vary the amplitude of this pulse. So the pulse here has a fixed duration, but a variable amplitude in this experiment. And we see that we can address different conductive states in these materials by playing with the pulse amplitude here. So, with experiments like that, we make a reset pulse, and then we make a set pulse or specific amplitude, and then after that we measure a static IV curve, but with a much lower voltages, not to affect the state. So the values are plotted here, and you see that we have kind of a resistive switching device where the higher resistivity it's obtained for states which are fully, let's say, either N polar or nitrogen polar, and let's say the lowest resistivity or the highest conductivity is obtained for the states which are partly switched here. And we put that on the domain wall formations. I will show you later on. We have done also similar experiments, but using only one single reset pulse, followed by a train of pulses of the same amplitude, but the number of them it's adding. So we have a pulse which has sufficient amplitude to switch fully, but it's a small duration. So then we add more of these pulses, and we can also follow this similar shape of the curve here by this cumulative switching here. Now we try to investigate more on that, so we put that on the formation of conductive domain walls. So in this experiment here, I will show you conductive IFM. So conductive IFM experiments combined with PFM experiments. In this case, the capacitors were pulled from the pristine metal polar to the nitrogen polar state by applying a voltage. Then, after that, the top electrode was removed chemically. And then these experiments have been done, so we performed PFM and topography, PFM and conductive IFM. And what is here very interesting is that when we have here, for instance, two domains, we have here, for instance, this N polar state, and this is a nitrogen polar state. We see a grain boundary here, which has much larger conductivity than the rest. Yeah, you see the profile here. So this has a much larger conductivity here at the boundary. So where the let's say the mixed domain volume is present. Yeah. And in this case, capacitor was switched back, and we see these are have more or less the same polarity, and they have much smaller difference here. And these things then, these capacitors then were investigated afterwards with the STM to see what happens microscopically in these systems.
You have 1 minute.
Okay. And we see that, for instance, we have in this region, which is partly switched, we have formation of head-to-head domain boundaries. They are inclined domain, which are known to be charged, so they contribute to the conductivity in this fields. Okay. So we put this behavior on the conductive domain walls formation, and we can build up a device out of that. Now I come to summary. So we see that these materials have an exceptional temperature stability. We have polycrystalline fiber texture films and epitaxial films. The films are periodic also in ultra thin regime, 4 nanometers. And we investigated what is the polarization state in Earth-grown films, and we saw that, for instance, those polycrystalline films are always nitrogen polar, Earth-grown, and the epitaxial films deposited on titanium nitride, they are metal polar, at least up to a certain thickness. And by introducing the platinum layer in these epitaxial systems, we reduce the leakage and lower the wave speed. And I think the most important result, we can develop a new type of membristic devices which are based on conductive relative domain walls, and those can be very interesting for neuromorphic computing application because they can mimic synaptic weights in the system. I'd like to thank two people contributed to this one. I mean, this is just part of those. Team in Kiel working on aluminum scan nitride, and Simon Fischer is the group leader. And thank you very much for your attention.
Question, please? From the point of view of electrical and optical property, how can you influence the band gap of this material?
Definitely doping is influencing the band gap in the material, but we didn't analyze into details this. So we didn't look in this, so we didn't investigate.
There are some literature data.
Definitely there's literature on that, but we are not focused on this.
On magnetic property,
yeah.
Once more. Question? I saw some measurements on polarization. I was just wondering, how do you perform that measurements?
Okay, so they are performed with the iExact system. So it's a theoretic analyzer. So basically, it's a fast IV curve which is running, and so the voltage it's scanned very fast. We use up to 100 kilohertz the frequency, and the current is measured. Dynamic current is measured. So and then this gives us these curves here that you see. This current curves which are required, and the polarization comes if you integrate these current curves. If they are integrated and then plot versus voltage, we get the classical polarization curve like this. So this is a standard method for measuring.
Maybe one question for me. Did you measure the dependence of the band gap from the thickness of the films?
Well, I mean, we really didn't look in the band gap. I mean, we didn't do any optical
characterization.
Characterization of those films. So far, I mean, we like to do that, but so far we didn't investigate this aspect.
More about electric
just exactly. Yeah, but definitely it's a very interesting point. So if we get the chance, we'd like to look into that aspect as well.
Thank you. Any question more? No? Thank you.
Yep.
We slightly changed the order of the presentations, and next presentation will be the BF regions mapping diffractive optical elements on gold-doped other polymer nanocomposites by polarization digital holographic microscopy, and the presenter is Veronika Kazak.
Hello, dear audience. I'm very happy to be here today. Thank you for the organization of such a nice conference with indeed very interesting papers coming from our visitors as well. We have made this paper together with our partners from Medical University from Turkey. We will discuss the birefringence imaging of diffractive optical elements on gold-doped polymer nanocomposites by polarization digital holographic microscopy. We have been investigating isopolymers and their photosensitive properties for a pretty long time, but since the recent 2 years, since we identified that these materials have very interesting anisotropic behavior, we decided to incorporate nanocomposites in this polymer thin films and see if we can increase, for example, our diffraction efficiency and in general optical properties of our polymers. And in this paper I will be presenting one small part of our research interest. So mainly we are interested in these materials because they offer us very versatile properties for recording diffractive optical elements, which is another part of our research interest. Mainly we are interested in developing diffractive optical elements that could be implemented in future, for example, in instrumentation, because we are also working with digital holographic microscopy. And many studies have shown that implementing these elements might increase, for example, the resolution or general performance of this instrument. And another key field which is of special research interest for us is digital holographic microscopy. Recently we managed to develop a polarization-sensitive digital holographic microscope, which is generally used for non-invasive investigation and three-dimensional imaging for different purposes. For example, for material science, or in future we intend to implement this instrument for biomedical imaging. So we will discuss four main topics. It's the fabrication of our nanocomposite polymers, the holographic recording of diffractive optical elements, the birefringence mapping of diffractive optical elements obtained on our nanocomposite polymers, and the method which was used to map the birefringence, the John matrix analysis. Here is presented our polarization holographic recording scheme, which we used to record our diffractive optical elements. We can classify direct holographic recording by scalar and vectorial holographic recording on films. We have identified that on our materials we can implement scalar holographic recording when we have the same polarization in object and reference beam in our scheme, and we have obtained pretty strong, pretty high amplitude of our elements. But we have also identified that we can perform holographic recording by using the different polarization of object and reference beam. In this case, we obtain not only strong amplitude, but we obtain a very strong phase modulation of these diffractive optical elements, meaning that we obtain polarization changing, or refractive index gratings, which have a very strong change in the refractive index. And here are some of our diffractive optical elements which we obtain. Using this technique we can obtain vortex diffractive optical elements, also superimposed diffractive optical elements. This is a very strong technique which can be used to obtain complex shapes of our elements, which means that, for example, as a perspective in the future, we could also probably manage to implement some diffractive neural networks on our materials. This is like a step forward for our research, which we plan to do. So mainly, For obtaining our isopolymers, we use the rod coating technique. We have investigated also the diffraction efficiency and the ellipticity evolution for different concentrations of gold nanocomposites in our thin films. So this is like the main scope of this paper was to identify how the concentration of gold nanoparticles influence on diffraction efficiency, on ellipticity, and on the birefringence of the diffractive optical elements. And as we notice, there is not a linear dependence. We have surface relief grating formation shown at different recording time periods, and we obtain the peak diffraction efficiency at approximately 8 minutes of recording of concentration between 0.2 and 0.6 micrograms per milliliter. And the higher diffraction efficiency that we obtain is actually achieved at 0.4 micrograms per milliliter. We also have very rapid ellipticity angle rotation at 44 degrees at the start of a recording, coincided with a recording of refractive index grating. And we have also identified post-exposure ellipticity changes indicating continuous molecular reorientation, which can be also linked to the matrix relaxation dynamics. For the investigation of the birefringence of our diffractive optical elements, we have built our polarization sensitive digital holographic microscope. This is actually a multifunctional digital holographic microscope, as we have both a polarization sensitive CCD camera and also a CMOS camera. That means that we can also identify the surface relief topography besides the birefringence, and we can use it both. By saying multifunctional, I mean that we can use it in also different modes. We have also a liquid crystal variable retarder, which is used when we have the phase shifting configuration. With this, we mainly use for the topography investigation. When we proceed to polarization investigation, then we switch to our polarization camera and to the off-axis mode, which was actually implemented for the results presented in this paper. We have a 640 nanometer polarized laser beam, which is focused and expanded. Then it's filtered by uniform collimation. Then we have the first half-wave plate, which regulates the transmitted intensities. And for the polarization acquisition, we perform actually several acquisitions. We have to acquire a hologram inside our diffractive optical element in first state of polarization at 0 degrees, and then we have to perform another acquisition in the region where there was it was not illuminated, so we call it the reference region. And for these two regions, we acquire both in two orthogonal half-wave plane orientations. And here is our the recorded hologram, which is inside our diffractive optical element. since I said that we perform the birefringence imaging in the off-axis regime, we use the fast Fourier transform for the reconstructing the phase maps and providing our complex optical field. Then to identify the birefringence, we perform our Jones matrix approximations. And here is what we obtain. We obtain our Jones matrix cross terms, and for identifying the birefringence, we actually subtract the phases in the Jones matrix cross terms. And by estimating the mean value, we can obtain the degree of change. And as we notice here, the maximum phase modulation, which we have identified, was for the 0.6 micrograms per milliliter of gold nanoparticles concentration in our materials. And here is like a summary of Jones matrix analysis. We have identified that the mean phase shift extracted from the Jones matrix diagonal elements show a clear dependence on the concentration and not a linear one. The key finding is that we have identified the optimal birefringence being at 0.6 microgram per milliliter, which has a maximum phase shift of approximately 3 radians and the highest diffraction efficiency of 27.5%. And above this concentration, the birefringence and diffraction efficiency actually decrease. We have also tried to estimate the dependence on the of the concentration on the height of the diffractive optical element. As we noticed in figure 6, we see that actually the highest
1 minute.
The highest pattern is observed at 1.2 micrograms per milliliters, but actually it has 2 peaks. And that's why we say that probably these peaks come from the change in the refractive index. So probably to estimate the height and the quality of our diffractive optical element isn't quite correct, since the contribution comes from 2 sides. And finally, in conclusion, I'd like to say that we managed to successfully perform the quantitative birefringence characterization of our materials, which was our main scope. We managed to identify the optimal parameters of nanoparticles concentrations for our photosensitive materials. And yeah, we really hope for future photonic applications of our instrument for biomedical science investigations. Thank you very much.
A question, please.
Are there any feedback to the laser from external circuit?
What do you mean by feedback?
Okay, you are sending him, then you have mirror, and the field is coming back to the laser.
Like a self-mixing effect. Yeah?
We haven't noticed that one.
There is no laser.
No, it is.
In the microscope, you mean?
No, I mean,
in the recording,
you have a laser.
Uh-huh.
Yes, and you have some circuit, external circuit. Within this circuit, some field, it's coming back to the laser or not? Usually you use some filter. Yes, you filtering.
Yes, no, this light not return in the laser.
It's not returning anything. Okay.
It was very poor energy.
Poor and diffractive in any angles.
Yeah, there is a loss of energy also on the diffractive pattern as well.
Yes, there are 2 possibilities. One is just you put a filter and then nothing will come back. The second, you just diffract the field to go outside of your system. Yes.
We have this task for our mapping of the regions. We study the materials, and various in materials depend on the illumination.
Thank you.
More questions?
What else? The questions, please.
How large are these gratings that are formed there?
What do you mean by the surface?
Yes.
Oh, okay. It depends also on the recording, but mostly it's half centimeters on half centimeter, right?
3 times. Okay.
It's small.
No questions more.
Yeah.
Well,
Thank you very much. Thank you.
Our next presentation, this is the direct and indirect transitions in the luminescence of stanium S2. And the reporter is Victor Zalomai.
Good afternoon. Let me introduce our work, direct and indirect transition in the luminescence spectra of stanium S2. Okay, why stanium S2? It's a two-dimensional multi-layered dichalcogenate nanomaterials are of interest because usually in graphene we have 0 band gap, yes, and could not use this in optic graphene. But with layered materials, one of is stanium S2, we can receive the single layer material, and this material has band gap. For this one, it's around 2 electron volts, 2.4 electron volts at room temperature. And what's happened? Due to one layer or few layers, 5, 8 layers, appears exciton, because the binding energy of excitons rise. Intense, usually it's 20 millielectron volts. When we have few layers, the binding energy of excitons becomes 200 millielectron volts or 500, depending of material. And if we received with such structures, we can use, because the mobility high, and we have, because the exciton is bosons, electron is fermions, and bosons take the one level of material, and we have some excitonic conductivity. Okay, this material can use in photovoltaic, ultra high frequency photosensors, field effect transistors, in thermoelectric phototransistors, and flexible photodetectors, and even in supercapacitors. Okay. It's present layered structures. Here is a structure and at the spectrum of this material. And here I show the layered structure of this material. Okay, we received by gas transport method, we received the, which one is?
Okay, we received the single crystals. Quite good, quite big. And by explanation, it's easy to receive some very thin layer of this material. And after that, we try to, by mechanical, try grinding these samples. First of all, received some micro sheets of this material. After that, by help of ultrasonic, we try to receive quantum dots or quantum sheets of this material. And here it's left image, it's single crystals, and right, we received some colloidal solution of this material, dissolved in water. Okay, few words about the single crystal properties, optical properties of this material. Here you can see absorption spectra of bulk material. This material has optical anisotropy because it depends for polarization. And here I show temperature shift of H. It's 8.3 for 10 in -4 electron volt per Kelvin, and this one, and we try to make usual optical spectra, absorption, and wavelength modulation, transmission spectra. We see the features were maxima which corresponding to direct and indirect transition in this material. Left side figure is indirect transition, right side it's a direct transition in this material. When we measure the photoluminescence of this material, we also see the indirect transition is the left side of spectra, and direct transition in these materials. Here it's a temperature dependence of this indirect transition in these materials. Also, one transition it's allowed in one polarization, another in another polarization. Okay. Here you can see the low temperature at 10 kelvins, spectra of photoluminescence and absorption. Absorption is not very good, but in photoluminescence we can see these two direct transition. And here we show this transition on the band structure image. Okay. In the case of these nano dots or nano sheets, I think nano sheets, in our colloidal solution, we received this in different parts of the cuvette, because we measured in the quartz cuvette, and in different parts of this cuvette, we measured photoluminescence. And you can see that B, C, D, F, G, F, H, and J, it's a spectra. I think it's spectra for different size of these nanosheets. It shifted to the high energy, because when the size of these nanosheets reduce, or quantum dots reduce, the energy rise, the energy of the transition, because we measured the direct transition in this material. And B, it's a low temperature of bulk material, low temperature photoluminescence spectra of bulk material.
Okay. The minimum band gap of this material, it's a direct material. It's a transition from L point to gamma point of Brouillon zone. Another indirect transition, it's from M to gamma point. And direct transition, we have we have an anisotropy, and it's a transition in gamma points in the center of Brouillon zone. In gamma points from a conduction band C1 to the valence band first and the second valence band, because it's by crystal field and spin orbital interaction with these valence bands usually instead of one valence band, by this spin orbital interaction and becomes free valence band. Okay. And the most intensive luminescence we observed in bulk material, we observed in approximately 3.3 electron volts, and can be associated to transition between conduction band C1 to the third valence band. And we produce some quantum dots on the base of this bulk material, and we think that luminescent spectra of valence band is due to direct transition in the center of Brouillon zone. Thank you for attention.
Question, please.
I have two questions. First is, do you have some studies or information how many layers can be in this, let's say, book, because where you can see this luminescence, and also do you take account about the surface of this sheet, if you understand my question? How many layers in the surface of this structure?
For luminescence, how big the surface is better for luminescence, because we have biggest signal for, yes? But if material has luminescence, we see luminescence not dependent how thick, how layers we have on this, for this material. But if we have 10 layers or less, the luminescence increases, and we can see the excitonic luminescence. And depending of amount of layers, the band gap is increases. Because for this material, I think usually if you have bulk, you have 2.3 electron volts. If you have 5 layers, you have 3.2 electron volts.
Okay, you can discuss a little bit when you have break. Other questions? If it's not the case, let's thank speaker again.
Thank you. One more question and one question.
No, yes.
I'd like to ask you the volume of these materials initially. This is anisotropic or isotropic?
Anisotropic.
Anisotropic as a crystal.
Yes, as a crystal, because we have unit cell. The distance we have B distance, it's around 1.4 nanometers. And here we have the distance something like 3-5 angstroms in this A and B. It's a orthorhombical crystal structure, and by this crystal structure, it's anisotropic for this B direction.
And after obtaining the nanoparticles or shifts,
nanosheets,
the anisotropy changed?
If we received very thin these nanosheets, anisotropy disappear.
Disappear.
Yeah.
Thank you. Thank you. Our next presentation is numerical simulation of the generation of picosecond pulses with gain switched DFB laser. And presenter is Veronika Dobrovolsky.
Good afternoon, ladies and gentlemen. So my name is Veronika Dobrovolsky. I'm a PhD student, and this report has been done in collaboration with Vasile Tronciu from Department of Physics, Technical University, and Hans Wenzel from Federman Braun Institute, Berlin, Germany. Outline, introduction, laser setup, model and equation, numerical results, and conclusion. We simulated the generation of picosecond pulses in gain switch DFB lasers using the traveling wave model. The results show pulses with a peak power of over around 1 watts and a pulse with less than 10 picosecond. And finally, we discussed the optimal parameters for application recurring short pulses. The picosecond optical pulse have important application in communication, seismic spectroscopy, material processing, and medicine. It's a compact, stable, and tunable pulsed laser source are essential for next generation diagnostics and therapeutic devices. The picosecond pulses can be generated by mode looking, Q switching, and gain switch. This work focuses on gain switch DFB lasers. And in this study, we investigate pulse characteristic and optimization for integration into miniatures Z medical and scientific systems. In this picture, we show the schematic view of gain switch DFB laser for generation of short pulses. So in this table we have the parameters used in this in our simulation of the gain switch DFB laser. This figure shows the in the panel A shape of injected current into active section in a single pass. What we mean a single pass? We increase the in the first 50 nanoseconds. We increase the current at 0 milliampere to 200 milliampere. The next 50 nanoseconds, we observe the current it's constant, and after 100 nanosecond, I mean 150 nanosecond, the current decrease at 200 milliampere to 0 milliamperes. In panel B, it's density. In first 15 nanoseconds, we observe the density it's increased, and
after around 100-150 nanosecond, the density dropped rapidly. In the panel C, we observed the evolution in time of output power for an injected current for the 200 milliampere. And this figure, it's a clean or it's a good pulse for our laser. And in panel D, evolution in time of output power for an injected current of 250 milliampere, we observe in this panel appear tails. When appear the tails, of course, the pulse it's not very clean and the energy it's not very perfect or good for our laser. This is the equation, the one time plus one space modeled for dimensional traveling wave equation for the slowly varying complex amplitudes. The next equation is where the relative propagation factor has this the form we used. And the next, it's the modal peak gain has a logarithmic form, and of course we use the polarization equation describes the microscope response on the active medium to the optical field. And the temporal evolution of the carrier density is described by this equation, by the rate equation. All these equations, of course, are incorporated in soft LDSL. The results and discussion in this figure, it's shown dependence of main characteristics of pulse, like peak power in panel A, full wave half maximum in panel of the same in panel A, total and pulse energy in panel B, and the delay in panel C. In the first panel, panel A, we observe when we increase the current, of course, increase and the peak power. But about full wave half maximum, it's higher in when we have the relative small injected current, 150 milliampere, and after when we observe when we increase the current, the full wave half maximum decreases. In the panel B, the total energy and pulse energy it's increasing when we increase the injected current, and then the last panel we observe the delay decreasing when we increase the injected current. Main parameters when we use, it's shown on this slide. So the next figure is the pulse characteristic on the dependence of width W of active region. So in the panel A, we have the peak power and full wave half maximum. We observe the peak power increase, and after relative short moments decreased. About full wave half maximum have a moment when increase, decreased, and also increase. Depends on the width. The panel B, it's about total energy and pulse energy decrease. And in the last panel, delay, if we compare with previous our slide, the delay
increasing from short width to long width in micrometers. And from this figure, in our conclusion, the optimal value for width to have a good energy and a good pulse, it's around 2 micrometers. In this figure, it shows the output pulses. It's a red line in dependence of pulse length for the trapezoid of injected current, black line. So, in the panel A, for the pulse length of 50 picoseconds, we have the current with or the
maximum.
The maximum for injected current, it's around 200 milliamperes. The panel B, its pulse length for 100 picosecond. We observe this. We have a good impulse. It's a clean impulse. For panel C and panel D, when we have length around 150 picosecond, 2 picosecond, we appear the tail, and of course in this case we don't have the good pulse for the laser and energy. So the next figure is the output pulse, red in dependence of rise and fall time of injected current, black. So for the first panel A, rise time, fall time, it's 25 picosecond. And we observe the output power. In this case, we obtain 1.1 watts. In the panel B, rise time and fall time, it's around 50 picosecond. The output power, it's around 1.4 or 5 watts. And the last panel, we obtain the output power 1.3 watts, but of course we observe it's appear the tails, so it's not very good value for our experiment or laser. The optimal value for the good pulse, it's if we observe from this figure, it's rise time, fall time around 50 picoseconds. In conclusion, we modulate the gain switch the lasers with traveling wave equation and then trapezoidal injection currents. The high currents results in a pulse tail. The best operating of a trapezoid length of injected current of approximately 100 picosecond is suitable, and we identify the best set of geometry and material parameters that yields to symmetric pulse with a full width at half maximum of less than 10 picosecond and high stability. And we believe that our work provides a good basis for future experimental study. The authors acknowledge the support of the National Institute project funded by the government of the Republic of Moldova. Thank you for your attention.
Question, please. I have a question. Maybe my question is very dilettante, but you say about the total energy and pulse energy. And what difference and how you differ this?
Total energy is shown in this picture.
Du-te la puls, parat puls. Napoj.
This. The pulse energy.
It's just pulse energy. It's just first energy of first pulse.
First pulse.
First pulse.
Ah, this is a
Yeah,
step
you
of
take full width at half maximum. You take the maximum and you multiply, and this is the pulse energy. Total energy, you integrate everything, which is just taking integral of this curve.
And depends on this position of pulse in the dependence of the form
Current.
of his...
Yes, of course.
Yeah, it's the good for us, this panel, the one we obtain the pulse and total energy.
Just one pulse.
Thank you. Once more question.
Maybe we allowed to sit down here, go to the last, because I've searched is a little bit, and then we come back to that. Așa zic, so let's go to the last, and then she will come with the...
Well, and scientific progress in perovskite materials, a game changer in photovoltaics. Yes, so this is the report now. Well, and reporter is Lyudmila Kazhikaru from the University of Tokyo.
Good evening, everybody. Thank you very much to be powerful until the last. I am very happy to be here, and today I am going to speak about scientific progress in the perovskite materials, which become recently a game changer in photovoltaics. So I am working at the moment as associate professor at the University of Tokyo, and I would like to, before starting scientific discussion, I would like to show you our campus. We are on the Komaba campus, so here we have some beautiful pictures. Now in October, the autumn season in Japan, so in our campus we have this nice yellow carpet of the leaf of ginkgo tree. So here you can see the leaf structure, or the design of the leaf is exactly the same like the logo of the University of Tokyo. So this is the symbol of our university. So if you want to reach Komaba campus, it's quite easy. From airport to Shibuya, and then from Shibuya a few stations. And you can have a chance to see also such a nice scenario in the campus. But in spite of such a nice nature, we also have a very nice team, inspiring team. This is our big boss, so Professor Hiroshi Segawa, who is hosting me since long time in his group. And then there it is additional sub-professor, sub-boss, and like this structure of the group. So I would like to thank him for hosting me. But I am born in Moldova, grown up here. I did my study at Moldova State University and then moved around the world, working in different fields. And basically, so my journey in science started in Japan actually in 2012, and then moved to Germany, then to France, and again to Japan. So I am material chemist, so I always synthesize the material in the laboratory and use this material, asking all the time myself how we can harvest the sunlight in the efficient way, cheap and sustainable. So Here is one example. Here I have one example of the solar cell that we built in the lab. So we didn't work only in the lab scale, but also move to the industrial, pre-industrial scale device. So here we have the solar cell, 10 by 10 square centimeter, 10 by 10 centimeter, or 100 square centimeter. So you can see this solar cell works in the diffuse light, which is actually different than we already know commercial silicon solar cells. So this device is based on two electrodes, negative electrode based on mesoporous titanium dioxide, and as you already know, titanium dioxide is white color. We cannot absorb the sunlight, that's why we need to attach on top the dye molecule, and then we need to, in this way we can absorb the sunlight. The positive electrode is based on the carbon, but can be metal, and here you have also the cross-sectional view. Probably it's not working this. You have cross-sectional view of this device, so you see mesoporosity, porosity of the titanium dioxide, and we have very large surface area. Why we need surface area? Because we need to absorb as much as possible dye to absorb more sunlight. And here we have different chemistry, how this dye is absorbed on titanium dioxide. And for me, as a researcher, it was quite easy to explain this technology for politicians, for example, because we can use different dye extracted from the fruits or from the tea. So actually you can extract the dye molecule at home when you are making the tea in the morning. So you can use that dye for synthesizing titanium dioxide and make your own solar cell. We also call this solar cell the artificial leaf. Why? Because the first step of the working mechanism is exactly like in the plant. First, in the plant, the chlorophyll is absorbing the sunlight. In this system, the mechanism is quite complicated, but the first step is absorption of the sunlight by the chlorophyll. And then inject the electron, and this electron is converted finally into chemical energy like food. In the solar cell, in this solar cell, we have the sunlight is absorbing, the dye molecule is absorbing the sunlight. Here you can watch the dye molecule getting excited. This electron is injected in conduction band of titanium dioxide. And then the electrode is extracted by the circuit, converting the electricity, and then regenerated the dye molecule by the couple electrolyte iodine minus iodine 3 minus couple. So you can see here is the complete system. We don't have any degradation of the material. So this is a circular process. So in this case, in the power conversion efficiency, at the moment we have a little bit over than 30%. So we are much better scientists than the artificial leaf. We can convert the sunlight 30%, over 30%. And as I already mentioned, we have so many advantages for this solar cell. We can make flexible, we can put in the house anywhere, and also we can change easily the color by changing the dye molecule. So you can see here different colorful solar cell with different print. So here we have this example. This was designed in 2012, thanks to the visit of François Hollande in our lab, and the print is his face in the manga style. Okay, so 2013, and even now we don't have any problem with these solar cells. So this is how it was made. Actually, I told you before, in the lab we work in the small size device. But once we have optimized the system by the material change properties, we pass to the pre-industrial scale. So here is the machine we use, made by Hitachi. You can see here in the video, the electrolyte is injected on the surface of the substrate, and this is very accurate because we need to count the amount of each droplet of the electrolyte, and in the case if the droplet is higher than the weight expected, the machine stops. So the precision is very high. Okay, so to assemble this solar cell, it takes about 30 seconds. Okay, very fast. So, but except that, we have also very good example when we come back in 2008, the product made by Sony. So here you can see very beautiful lamp. But this work, unfortunately, it was stopped, and yes, because of some issue. And also we have one example when this solar cell helped the tsunami victims when it happened in 2011. So the people could not have access to the electricity. That's why this solar cell charged during the day the battery, and during the night the people could use. So this is not AI picture, it's a real picture. So of course the science doesn't stop here. So we continue to work on this direction. And one of the questions we had at that time, it was how we can solidify this solar cell, because inside is liquid electrolyte and can easily evaporate or leak outside. Okay, so we use then polymer type or organic material which replace the electrolyte, and in that case we need to decrease the thickness of titanium dioxide a lot, because this molecule, it is a polymer and cannot infiltrate inside of such a thick mesoporous titanium dioxide. And in this way the perovskite material was came in the field. So this is a turning point. Then we discovered perovskite material. So at the moment the power conversion efficiency of the perovskite solar cells go up to 27%. So if we are looking back early history of perovskite material, in a very long time ago, calcium titanate was discovered by Lev Perovsky, the Russian mineralogist, and he was looking the properties of calcium titanate, and this is oxide perovskite structure. So the name of the crystal structure came from the Russian mineralogist. Later on, by changing calcium with methylamine and titanium with Pb and oxygen by bromide, David Mitya, USA researcher, proposed organic-inorganic hybrid perovskite. So we keep the same crystal structure, that's why the name remains the same. And the first time used for photovoltaic application of this material, it was in 2005-2006 by a PhD student of Professor Miyasaka from the University of Tokyo, and they could prove that this material has very good property for photovoltaics. And that was amazing, because at that time the power conversion efficiency, it was just 3.8%, but the device was liquid state. So he could not measure the device he have to measure the device very fast. So nobody believed he is going to get his PhD at that time, but he still continued, and the breakthrough came in the field when instead of liquid electrolyte, it was used this spirometalled material, which works as solid whole transport layer. So here you have the cross-sectional view of the device. There we have mesoporous titanium dioxide and also perovskite infiltrated inside, and keeping this whole transport layer, which is also solid type. So we have then whole structure perovskite solar cell. So now here the perovskite hit the power conversion efficiency over 27%, and you can see how it go up over the year, and the power conversion efficiency from starting in 2012 from 10% and now 27%, and quite short time of development. And we have never seen any solar cell technology such a kind of fast growth. So this is really amazing material, and it's reaching the same level like commercial silicon solar cells. I also started working in the field quite early stage while working in Japan. So here you can see also my first device was very poor, just 3%, but in quite short time I could improve the efficiency and jumping up to over 10%. You can see the device 1.5 by 2.5 centimeter, which is really small, lab scale, but I could then jump further to 16%, because I use special equipment in Japan. So here we could keep the dry conditions, because making perovskite solar cell we need special conditions, because this material cannot easily be grown and normal relative humidity. So this is dry room we call, where we keep all our equipments, but also the processing. So at that time in 2014 I could get the top record efficiency in Japan, and then move to the large scale, like 10 by 10, the same size. And there, the video, you can see the perovskite solar cells working quite well under the solar simulator. And to make this device is also quite simple. We need the conductive substrate. Sorry. So on what we spray for spin coat titanium dioxide, N-type layer, then spin coat perovskite layer, and then on top of that we spin coat spirometab layer, which is P-type material, and complete the device by gold evaporation. So here you can see the cross-sectional view of my device. You see perovskite layer, CH3 and H3, PBA3, have just 350 millimeter thickness. And when we are looking in case of commercial silicon solar cells, the process is quite complicated, so we need a really high temperature. In case of perovskite, the highest temperature we make for perovskite is around 150 degrees C. So our process is very fast and also printable technology. Finally, the silicon is 300,000 nanometer, 1,000 nanometer higher thickness compared to perovskite. So now you can imagine how this thin technology can produce the same efficiency like silicon solar cell. But why this happened? Because perovskite solar cells have so interesting physical properties, because it is a direct band gap. So we have intense light absorption. So here you can see in between 400 nanometer to about 800 nanometer, we have very nice flat region of absorption. And because of this sharp absorption edge is direct transition, and also we have high absorption coefficient, we don't need too much thick film, and also we can tune the band gap by changing the composition. So we can play with the cation side, or we can play with the anion side. So in that case we can change the color and the band gap. Another big bonus of this solar cell is that even they are not perfect crystal, they can behave very well. So we don't need to make very high quality crystal to make efficient solar cells. So, and another interesting property of the solar cell is that they can work well even in the low light intensity conditions. So we also published that in 2017, such a interesting response of the low light intensity. And in Japan, adopted the findings, this technology. So in COP28, the Prime Minister of Japan mentioned about the perovskite solar cell. The keyword it was perovskite. So I hope he understands what is that. And also the huge funding was especially directed to green innovation projects. And one of these projects is the funding was going to the perovskite solar cell. So you can see the amount of money invested in Japan for development of this technology. And University of Tokyo, our group is the managing the project, and what we have several companies working on, Toshiba, Sekisui, Naishin. So you already probably knew about the exposition in Osaka this year. So very soon it's going to be end. And here in this exposition there are so many future technology displayed. And we have also one example for perovskite solar cell installed in the bus station, about 250 meter of the panels installed. That was done by Sekisui chemical company, but also we have some example for the design. There is the Panasonic, who is working for the design of this solar cell, or Aishin, the branch sister company of Toyota. They also have some panels already installed in some buildings. Now, the problem of the solar cell that we are working on is the stability. So this material can be, in the laboratory scale it's already proved about 1,000 hours, but that is not enough, so we need to work hard to improve the stability and reach the same level like commercial silicon solar cell. So that is one. And the second one, in the European regulation, we have to consider that LED is not allowed in electronic device. So that is another issue. What all the researchers in the field are working in that technology. And my personal work is I want to propose a new material for changing the perovskite or beyond perovskite solar cells. And now I am focusing in silver bismuth S2. And at the moment I have the already processing of this material by solution process using the same method like I was using in perovskite. And the efficiency I got so far at 6.3, 6.8 is stabilized efficiency. And this material has a very good future because we can predict theoretical efficiency over 20% with very good stability. So you can see here the plot of my data. And probably you say, okay, it's not enough, 6.8, but we don't see any, in this general chart, we don't see any technology going down in the efficiency, it's always going up. So I am very positive for that. Okay, so, and that is the conclusion. What I want, I was thinking there are some students, so I wanted to say that the research is journeying, so we always keep changing, facing challenges, but always move forward toward discovery and process. So thank you very much for your attention.
A question, please.
What about the prices of Germany?
Yes, so at the moment they are the business is not yet open because the technology is under the testing conditions. So I hope once they are going to prove the stability and all this issue, and I am sure Japan can succeed because they have very high technology. So they are working in this direction to improve the stability or seeding material for making a device as powerful as commercial silicon solar cells. And then the prices, I hope, much lower because the processing, it's like the temperature we need is below 150 degrees. In case of silicon, we need to think about the high temperature for fabrication of high quality silicon crystal.
What kind of soft you are using for theoretical prediction?
It's just a rough calculation by knowing the band gap of the material.
It's just done by you?
Yes.
Yeah, in terms of cost, silicon, I'm afraid, is difficult to beat because it's in the solar cell not the main cost driver anymore. So whatever, instead of a plastic plate for a roof, it's cheaper to put a solar cell even if you don't connect it. If you connect it, you get the price out in 1 year. So therefore I heard that for perovskite cells it could be very interesting, and I think this is also in the solar roadmap, to have this as a kind of double layer tandem cell. So what is your opinion in this direction? Because then you would save all the infrastructure and then you can play the advantages of printing and so on.
Yes, I think this is another direction tandem. I didn't speak today because of very time. You see, I was rushing, you know. So
you have time now.
Yes. You know, tandem application is also a very interesting approach to go further for the efficiency. Also, knowing the efficiency is going up and the price, of course, will go down. I believe if we consider such a calculations. And but that depends on the application. For example, if we are speaking about only perovskite, having 27%, and if they are flexible, if they are quite stable, so we can put, for example, on the wall, which silicon cannot be used, or in the window, or inside in the house. So
okay, yeah, but the other one might be in the big market kind of the silicon. Because then in future, from 35 on, every solar cell has then a perovskite layer on top in order to be at the whatever 38 or 42%.
Yeah, prediction is over 42%, which is really amazing, and yeah, it can be very interesting for the future.
Yeah, and your bismuth variant, is it similar in terms of band gap?
The band gap is around 1.0 or 0.9. So what I am doing now on the lab is in between 0.9 and 1.2. And very interesting for me because nobody succeeded to make a solution process. It's quantum dot already people use. So making quantum dot is quite a long process and we need time and commercially cannot be done. But in this case it's printable, so it can be printed in many different large scale solar cells.
Thank you.
One question.
titanium oxide has a very big index of refraction. And you have anti-reflection cover of your cell.
In this solar cell, this is a dye solar cell. In this case, we don't have. But of course, to increase the GC, we are going to do anti-reflection layer. For example, fluorine, fluoride, some material.
Because this is vacuum technology.
Sorry.
The anti-reflection coating is vacuum coating.
Yes, yes, yeah.
So this technology is complex.
So I cannot enter into the detail what each company in Japan is doing because I am not, how to say, direct in the lab. But of course, it's very complex question now. So anti-reflection is really needed for high efficiency. Okay, this is you can increase the efficiency for 1%, 2% if you are doing the anti-reflection coating. But if there is suppose that we have some material which can be just printed or just sticked on the surface of the glass, then we can increase the current and the efficiency of the solar cell. So I'm sure companies are thinking about that, how to increase the efficiency. Because another problem is in the lab scale we have the efficiency quite high, around 27–25% of the perovskite, but when we pass to the big technology, to the scaling up, then the efficiency is really getting lower. So now the modules, they are around 80%, so Panasonic proved 80% for large scale perovskite solar cell. So there are some still issue, but the company are doing hard work in that direction.
What is the theoretical limit of efficiency for perovskites?
For perovskite, I think also around 40–42%. Yes.
And is it possible to make something like multi-junction solar cells?
Yes, this is the same questions like I got before. Tandem application is one of the tandem solar cell is one of the next or direction.
But tandem, is it limited by two layers, two kinds of wavelengths? Or maybe 2, 3, 5, and so on.
Yes, yes. So we really need to think about how we can design this tandem solar cell. What part of the spectrum we want to absorb? Okay. So, for example, if we put perovskite, we have this range of absorption from 400 to 800. So this means in order to extend our absorption from the solar spectrum, we need some material with this band gap, okay, or this band gap, in order to absorb whole spectrum of the solar spectrum. We need to really think about what kind of band gap material we put together to absorb maximum sunlight.
So you can't use simply different dyes for sensitizing?
For sensitizing a solar cell, I think at the moment people already give up. Because the problem of this technology is the liquid electrolyte. So they are so beautiful, we enjoy very much this time. So here I already show you the story in the back. Here, this period of time, all of us are missing because that was one of the technologies and we really could speak with the people. So you can see it's so beautiful. So everybody enjoyed such. If we change the color or if we change the print, we can easily show to the people, or even at home you can make, or even for the school, for teaching, for education purpose. But the problem is that the efficiency is still low for this solar cell, and the people are still working, some of the people, but some researchers, but they already give up because perovskite is much more attractive at the moment. Okay. So in the dye cell, of course, that can be probably put in somehow tandem. I don't have the example at the moment. Probably there are some more because I already left this part of the research before, so I focus all the time perovskite.
What are the real prospects to solve the problem with the stability of perovskite?
Yes, so this is one of the issues that we are facing now, working hard in order to understand, first of all, what is the mechanism of the degradation. It's really because of perovskite, or it's really because of the interface. So in this solar cell you can see we have several interfaces, and sometimes we have different thermal expansion coefficient, and this can be easily filled up or disconnect, and then that also affects. So this is the first, we want to understand what is the problem. And the second one, in order to improve the stability, we need to seal the device quite well, which is really tough work at the moment. So companies...
This will cost?
So, yes, so if we add another material, it may cost, of course. But if we can, by the cost, we can increase the lifetime of the solar cell, I think we can gain the cost as well, I mean, yeah. So I think the cost calculation is also related, lifetime and the efficiency. So we need to consider all this together.
I observe GSPS. Is still this fellowship available for our young people?
Yes, so this is also was very new to me at that time. I didn't know that it exists. I could have GSPS in 2012 until 2014 by applying from French side, because I did my PhD in France, and then because of the diploma from France I could submit my proposal GSPS in France office. And even now exists this GSPS, very, very powerful funding.
It's for young people.
There are for postdocs and for short-term mobility also.
I was there for 2 years.
Yes, me too, yes, me too.
But my interest is just to look for some young people to be sent there.
Yes, it's still existing, very high competition to get it. And, but it's...
It is possible.
Yes.
Thank you.
I don't know where is the office of GSPS here, where you can submit the applications. Directly to the GSPS, yeah. Yes. It's a very good chance for students.
Thank you.
And
okay. Veronica.
Our last presentation is...
We made a little bit changes.
Yeah. Numerical investigation properties of picosecond.
It's another mechanism.
And the same report.
Yeah.
My next topic, report, numerical investigation of properties of picosecond pulses in indium-gallium lasers under Q-switching operation. This report has been done in cooperation with, of course, Vasile Tronciu and Spiridon Rusu. Outline is the same, introduction, laser setup, model and equation, principle of pulse generation, numerical results and conclusion. We present a theoretical study of picosecond pulse generation in blue-violet indium-gallium semiconductor laser with a saturable absorber under Q-switching mechanism, and the results highlight optimal design conditions of demonstrate the potential of indium-gallium Q-switching laser as compact high-performance pulsed source for application in medical diagnostics, imaging, dermatology, etc. Picosecond optical pulse have been widely studied due to the important and advanced technology, for example, in free space optical communication, bioanalytics, time-resolved spectroscopy, sensing and LiDAR, material processing, medicine, etc. Blue-violet gallium, indium-gallium laser enable compact, high-performance picosecond source. Since recent studies demonstrate the generation of sub-10 picosecond pulse with a high peak power and energy, and this sort investigates Q-switching indium-gallium laser through theoretical modeling and simulation, focusing on pulse characteristics such as peak power, energy, and width. In this picture, we have the schematic cross-sectional view of an indium-gallium laser with two applied current, J1 and J2. J1 is for the active region and J2 is for the saturable absorber. The active region extends the full length of device. This.
And on the other hand, the saturable absorber is grown in the outer regions on the laser, and the substrate is the gallium structure. This we have the equation. We use the single mode model, which after mathematical transformation is given by the following rate equation for photon number and a dimensional injected current, and number N1 in active region and N2 in saturable absorber. We use a dimensional gain saturation coefficient and threshold gain level. In this figure, show the principle of pulse generation. In panel A, it's current injected into active. It's represented in red line, and in saturable absorber, it's black line section in this red line. Yes. In panel B, it's generated output pulse, and this zoom, it's the inside shows zoomed pulse. And if we observe, we obtain the pulse at 2.99, 3.101 nanosecond with injected with a current with a power around 116 plus minus watts. And this figure illustrates how the peak of the pulse in panel A. In panel B we have the pulse width. In C we have the total and pulse energy, and in D we have the delay. How change these parameters when we change the length for saturable absorber? If we observe in the first panel, panel A, if we the power it's increased when we have a short saturable absorber, and when we increase the saturable absorber, the power it's decreases. In the next panel B, it's pulse width. It's the first it's small pulse when we increase the saturable absorber, and around at 200 micrometers the pulse width observed it's increased immediately. In the panel C, above total energy and pulse energy, when we have the short saturable absorber, we have the high total energy and pulse energy, and when we increase the saturable absorber, decrease the total and pulse energy. And about the last panel, we increase the saturable absorber, increase the delay, in the next figure show the dependence of the main characteristics of pulses similar to those presented in previous figure. Above, independent of total losses in the device. It's clear this when we have higher losses, we obtain practical zero results or nothing. This it's the figure illustrates the effect of back facet reflectivity on pulse characteristics with fixed front facet reflectivity. The pulse are not generated at very low reflectivity while a slight increase in change peak power, energy, and full wave half maximum. At higher reflectivity, total and pulse energy decrease, the full wave half maximum increase monotonically, and the pulse shape evolves from nearly symmetric, from low reflectivity to asymmetric or high reflectivity. And it's shown in this panel. And in the first panel, panel A, we observe the pulse. We zoomed the pulse, and a good pulse we obtain when we have relative low reflectivity, around 0.1, 0.2. In conclusion, we can say the picosecond pulse is generated in indium gallium laser with saturable absorber via the switching were analyzed. The saturable absorber length strongly influences pulse features. Longer saturable absorber decreases energy and peak power. When we have the back reflectivity, if we have too small back reflectivity, we don't have the pulse. If we have the large back reflectivity, of course, we don't have the good results. The optimal value to obtain the good results, it's 0.1 for back reflectivity. It's for optimal energy and symmetry. And the optimal parameters for the laser, it's wavelength 405 nanometers, saturable absorber, I told it's around 200 micrometer. The reflectivity is 0.1 or 0.2, and losses it's less 2 meter power -1. And the results provide a solid basis for future experimental studies of blue indium gallium lasers with the saturable absorber. Thank you for your attention.
Do you have any questions?
What is the difference between gain switch and Q switch?
About the energy...
Two different mechanisms.
But where it is better to use one mechanism and where another one?
In the first, you mean the first...
It depends on the applications.
In which applications?
In medicine? No. In medicine, it's better to use such.
With
indium gallium yes. If you go to space communication, then you go to gain switching. Avem 400 de nanometri și acolo.
Any question more?
What do you mean single mode? And first slide was single mode.
Single mode, we mean
What
we
about
injected
It's just
about beam or about calculation?
No, it's just a single mode operation of laser, and this is done due to distributed feedback, which select only one mode which is operating.
But transfer or
longitudinal. Longitudinal.
No?
Thank you.
Thank you once more.
Thank you very much for everybody being here, and have a nice evening, and see you tomorrow here again, because we will continue tomorrow our work. Even it's raining, it's still, but maybe tomorrow